Let's begin. Okay, are you ready for another prank? No. That's it. It's once in a lifetime. And Zach was telling me I cannot do it next year anymore because you guys are going to tell everyone. So I have to wait 5 years, now 4 years, to do it again. That's going to be fun. Anyway, so I wanted to remind you your exam is on next Tuesday. And it's going to be exactly in a similar spirit as exam 1. You'll have essay questions and a bunch of multiple choice questions. You'll have to exercise understanding, comprehension of like when to use the T distribution, when to use the F distribution, when you're comparing two populations, etc. So a lot of thought process going on. There will be a few calculation problems. You're welcome to use your Excel or Google Sheets. So if you want to set up like calculators for different configurations, etc., feel free to do that. All the power to you. And because I want to focus more, emphasize understanding of how we're using statistics. And I wanted to check in with you if you'd like on Thursday, if you'd like to have the Q&A session together. We used to do this in numerical methods, and I don't know, I'd like to think they were helpful, those sessions. So if you'd like, we can dedicate some or all of Thursday's class to do a Q&A with you. Some of you are already starting to fill in the survey on Canvas. So by Thursday, I'd expect most of you to have done it already. So, who would like, let's do see some hands. Who would like to do Q&A on Thursdays? Thursday? Okay, so I do see a majority. Okay, so we'll do that on Thursday. This is the only thing you get to vote for in this class. So we'll do Q&A on Thursday. Just come prepared, okay, and put your questions on the survey as well. I'd appreciate that, so at least I can see them before coming in. And you're welcome to interact in the class with me and ask any questions you have. So we will be covering on the exam primarily central limit theorem, confidence intervals for one population, and confidence interval for two populations. Obviously, I mentioned this, knowledge of continuous distributions in the sense that we're using continuous distributions in all of these applications. So understand the difference between the F and the PDF, calculating area to the left, to the right, etc. Those basic things, right? But don't, it's not going to be as intense as exam 1 on questions on continuous probability distributions. Okay. I would like to continue with hypothesis testing, but I want to share with you a piece of what happened here. At least it's okay. Okay, this is better, I think, because anyway. So someone tried to fix it, but it's a little bit better than last time. So I know you guys might appreciate it or might not, but sometimes I like to share a piece of thing I thought about or that motivated me with you. Some of you appreciate that. Some of you don't, but I still like to share it. So I was watching the other day, who's into rowing, like professional, what do you call it? Rowing? Yeah, boats. Like who watches that stuff? Anybody like sits down, like look at them, like, right? It's like such a, out there sport. Yeah, some people do it, and it's like insanely intense. If you tried a rowing machine at the gym, you come out like this. The next day you can't walk, you can't stand up. I tried it a couple of times. Very intense, very functional, I think. And so we turned on Netflix the other day, and my wife was like, "Oh, we should watch that movie. It's about rowing called Heart of Champions. If you've seen it." And she was like, "I think I watched it on the airplane." I was like, "There's like what in the world since movies started? There's like 2 movies about rowing, right? But apparently there's one other movie. Well, it was such a good movie. It's like one of those things where, like reading Dostoevsky, you cannot unthink about it for a month or a year, right? Just like you keep thinking about it. But what struck me in that movie, there's always in those movies about sports, there's also movies about baseball and soccer and whatever, and you get this team who's struggling and they're like fighting with each other and they lose, and then this coach comes in and asks them, "Why are you doing this?" Or like, "To win the game." "No, why are you doing this?" etc. And starts torturing them with like exercising and working out and doing this and doing that, and then they win, right? and you leave that movie like, darn it, this is awesome, right? You leave motivated, you leave happy, you have a smile on your face, right? Isn't that true? Do you agree with that? Yet, you don't apply that to your own life. We don't apply that to our own lives. If somebody is torturing me with work that I have to do, that I know at the end I'm going to come out 10 times better, right? I'm like, I don't see the end, right? I don't see that. Same thing when you get like homework and exams, right, from your different professors and different courses. You're like, oh, why do I have to do this? And I don't want to do that, right? Maybe next time you see that, think about those movies. Think about the end. What happens when, watch yourself as if you're in a movie and your teacher is the coach and giving you these exercises because hopefully they have your best interest in mind, right? They've seen the end before and they want you to get there, right? So maybe see it from that perspective and put a smile on your face and just do the thing, right? Just do the thing. Apply that movie concept to our own lives, right? Okay, so that's the spiel for today. Let's get back to hypothesis testing for a single population. So last time we demonstrated that your colleagues were not cheating. We took their similarity score and assumed that the average similarity score in the class was like what, 33%. They had a similarity score of 37%. What's the probability of that occurring if the average score is 33%? We did a normal distribution, right, because those are samples distributed normally, and the probability of seeing that result was, what, 11%, 21%. Everybody said that's a very high probability, so it's probably just pure chance. And again, I always tell you with hypothesis testing, go back to the example of flipping a coin. I give you a coin and I tell you it's fair. You're going to assume that you're going to get 50% heads, 50% tails. So you flip it 100 times, you get 48% heads and 52 tails. You're going to be like, yeah, this is still fair. But if you get 40 heads and 60 tails, you start becoming suspicious. If you get 30 heads and 70 tails, that's very unlikely. It probably means that the coin was not fair in the first place. So a hypothesis test is a statement about your belief on the population, not on the sample, about your belief about the population. Whether your assumed mean value or variance, those are like the two things, or proportion, is true or not, okay? Now, hypothesis testing is not that different from confidence intervals, and your colleague asked me the other day, like, yeah, what's really the difference? The framing of hypothesis testing is more conducive to scientific thinking, the scientific process. You test the hypothesis, you collect evidence for it. But in the end, you can bring it down back to confidence intervals. And another way to think about it is you collect a sample and you can compute a confidence interval on that sample to estimate the mean of the population. If that estimate does not contain your assumed mean, it means that sample belongs to a different population, to the population of unfair coins or the population of students who were cheating, right? That's how one other way to think about it from the perspective of confidence intervals. All right, so we did all of this. I'll go through it a little quicker this time. And this is what I introduced, the hypothesis testing. If you have an assumption or a belief about the population, shown in mu here in red, and we call this the null hypothesis. That's your belief, that's your assumption about the population. It could be a mean value, it could be a proportion, it could be a variance. And then you ask your question, you go grab a sample, and you compute the sample mean or the sample variance or the sample proportion. How likely is this to occur? Again, flip the coin. You get 30 heads, but you assume that the coin is fair. How likely, with a fair coin, how likely is it to get 30 heads? Very unlikely, right? And then you would deduce that the coin is not fair. Okay, so it's still an inference about the population, statistical inference, going from sample to a population. There are 4 steps we discussed last time. First, you have to identify the null and alternative hypotheses. So the alternative hypothesis is your research hypothesis, saying either the true mean is less than the assumed mean or greater than the assumed mean or different than the assumed mean. There's only three options. And then you determine which distribution you have to use to do the test. So if you have a population with a known sigma, you use the standard normal distribution. If you have a population with an unknown sigma, you use the t distribution. If you have a proportion, you use the standard normal distribution. And if you have a variance, you use the chi-squared distribution. Those are the distributions we learned, and quite sufficient. You gather data. We're not going to do that. We're going to be given data, and then you calculate the sample statistic, which is either the z value, the t value, or the chi-squared value, and then finally draw a conclusion and say, do we have evidence to keep the null hypothesis or reject it? Again, we'll go through that again. We'll do this with an example, and I'll repeat this briefly here. Based on historical data, the Board of Education for one large school district believes that the percentage of high school sophomores considering dropping out of school is 10%. So their faith, their belief about the population is that on average, the average number of students dropping out is 10%. A high school counselor in the district claims that this percentage is too high. And so he's seeing students come into his office and he's talking to them, and he thinks, no, it's not 10%. What I'm seeing is less than 10%, maybe 8%, maybe 7%. It's definitely not 10%, it's less. And so he collects a random sample of 50 sophomores and finds that 8.5% of them have considered dropping out of school. So we need to perform a hypothesis test on this with this significance level, which we're going to introduce in a minute, what that means. So the first step is to identify and clearly state the hypotheses. There's only two hypotheses, a null hypothesis and a research hypothesis. The null is always your belief about the population. In our case, the null hypothesis is that the school dropout proportion is 10%, or p equals 0.1. Okay? The null hypothesis is always designated as H0 or H0, and it is always a statement of equality. P equals something, mu equals something, sigma squared equals something, or sigma equals something. It's always a statement of equality. It's just an assumption about the population. Coin is fair, proportion of heads is 50%. Okay? HA, or alternative hypothesis, describes the population parameter that the researcher is trying to collect evidence for. So in this case, the research hypothesis or the alternative hypothesis is that the actual proportion is less than what our belief is. Always, the right-hand side of your research hypothesis is the same as your right-hand side of your null hypothesis. So you start with a null hypothesis and then determine if you need to be less than or greater or different than that number. Okay? There's three options for the alternative hypothesis: either less than your belief in the population, or greater than your belief, or not equal to your belief. Okay? So mathematically, we'll represent these as you only have these options. Always for the null hypothesis, you're making a claim. Mu is equal some value, or p is equal some value, p0 let's call it, or sigma squared equals some value, sigma 0 squared, okay, for the null hypothesis. Then the alternative hypothesis is that, no, that belief is wrong. Either the true mean is less than this value we assumed, or it's greater than that value, or it's just different than that value. Okay? And we'll see this is going to be the most interesting here. Okay? Now, for the alternative hypothesis, you only pick one of those. Okay? You can't have three of them together. Okay? You just pick one of those. Okay? The next step is to determine which distribution to use for what we call the test statistic. So, and I'll explain that in a second. We know these three distributions, really. If you're looking at the mean value and you know the standard deviation, then you use the normal distribution. If you don't know the standard deviation, you use the t distribution. If you have a population proportion, if that's kind of what you're looking at, then you work with the normal distribution. And then if you're looking at a variance, you're comparing variances and your hypothesis, you look at the chi-squared. Now, these are my test statistics, or the test statistics. So when I say in this hypothesis, the test statistic is a t-score, it's just a way to standardize the value that I'm given. So if you think about it, you have a presumed mu, you have your x bar measured from the sample, You have either the sigma from the population or S from the sample. And so you have all of these values. You convert them to a t-score or a z-score or a chi-squared score to just standardize the analysis. Because in the end, what I said earlier is still true in hypothesis testing. What's the probability of getting 30 heads out of 100 in a fair coin? So the way we're doing this, we're going to convert that, getting 30 heads, we're going to convert that into a z-score and just work with the z distribution. Okay, that's it. That's why we convert everything into these standardized variables, whether standard normal or the t distribution or the chi-squared, just to simplify the analysis. But it's still true. We're looking for the probability of getting that sample given that belief in the population. Okay? And then we would have to also determine a level of significance. So once you determine a test statistic, you must decide on a level of significance for the test. So that's your threshold, in a way, that's your threshold of what is acceptable in a, what's acceptable to really say that, no, this is not good. Like, okay, is the probability of getting 30 heads, what if you get a probability of 5%? Is that acceptable or not? If it's acceptable, that's your level of significance. What's your how much can you tolerate? 21% for the similarity score. Well, you know, that's definitely not beyond the norm. 21% is a very high probability. Okay, so really that level of significance is the probability of getting such an extreme value to say that this is not random chance. Getting 48 heads or 45 heads, that's probably just due to random chance. Okay, but you might tighten your significance level and say, no, I want to make sure that this event is so rare that, you know, I want to rule out any other factors. And I gave you an example last time in physics. To discover a new particle, the probability of finding that particle is like 3 times 10 to the minus 16 or something. That's their level of significance. If the probability of finding that is so low, is below that value, then it is a new particle. Okay? So think about the coin, think about the cheating example. The probability of their score was 21%. That's too high. But what is too low? Maybe we could say if their similarity score is less than 1%, the probability of getting that score is 1% or less, then that's very, very rare. And then we're going to say that they're cheating, okay? So for the example we were working with, I give this discussion here, like what would it take to convince you that this is so rare? And then I introduced statistical significance, which I essentially discussed just now. A sample statistic is statistically significant if it is far enough from the presumed null hypothesis, okay, to conclude that it would be unlikely for the sample statistic associated with the sample to occur through pure chance. In other words, is the likelihood of getting that sample so low? If it is so low, then probably the null hypothesis is wrong. Okay? If the probability of getting if the probability of getting 30 heads is so low, it means the coin is not fair. Okay? Again, switch it back to the coin. And I give this example of the coin over here, and also try to tie it to a confidence interval. All right. So now if C is how confident we are to have captured a true parameter, so say C is 99%, just like what we did with the confidence level and confidence intervals, then alpha, which we also discussed last time, which was 1 minus C, alpha is the probability that we did not capture the true parameter. So therefore, alpha is therefore our level of significance. So level of confidence, and remember carefully, level of confidence is how confident we are in getting that confidence interval. It doesn't mean that there's a 95% chance of finding the mean value in the confidence interval. It only means that if I take 95 out of 100 samples, they're all going to get the same confidence, and the mean is going to be in their confidence intervals. Okay? It doesn't mean the probability of the mean value is in that confidence interval. Same thing for the alpha parameter. It's the probability or the chance we did not capture that true parameter. Okay? Another way, weird way of framing it, is to say that alpha is the probability of making an error of rejecting a true null hypothesis. So if the coin was indeed fair, but then my analysis concludes that I say, no, the coin is fair, but it is truly fair, I've committed an error there, and alpha is that probability, is 1 minus the confidence level. Okay? Now, you want that alpha to be small, because you don't want to commit an error. This is called type 1 error, which we will discuss later. But you don't want to commit this error, so you want alpha to be small. But you cannot make it very small, like I said last time, because there's another type of error which balances out with this alpha error, and we'll talk about that later. Let's just get through the mechanics first. So from now on, alpha is called the level of significance. So somebody might tell you, hey, here's the confidence level or the significance level. You always have, when you're doing hypothesis testing, always go to alpha or a significance level. All right, so for example, for our example, we need to use a normal distribution, because the sample was greater than 30, so we got 50 students, and the significance level actually is for different conditions. NP and n times 1 minus p have to be greater than 10, and that's satisfied, so we can use a normal distribution for the proportion, and the level of significance was given to us at 0.02. Okay, in other words, the confidence was 98%. Finally, gather the data and calculate the sample statistic. We already gathered the data. The counselor did that for us, and he gave us the numbers. So for our example, the sample statistic is simply a z-score based on proportions. P hat is the sample proportion, which was out of the 50 students, 8.5% wanted to drop out. So the P hat is 0.085, and the population proportion, our belief in the population was 0.1 or 10%. So you just run a number, just nothing but a calculation. So what this is doing here, it's converting the sample into a z-value on a standard normal curve. So then we can start making analysis on the standard normal distribution. Okay, simplifies all the analysis. That was our null hypothesis, right? So that's our belief that 10% of students were dropping out, right? Okay. Okay, this is screwed up here. Okay, so finally we have to draw a conclusion and interpret the result. So throughout the hypothesis test, you are assuming that the null hypothesis is true, because that's your belief about the population. I'm assuming that the coin is fair. I'm assuming that students are cheating. The similarity score is 33%. Okay, you believe that only 10% of students are dropping out. Okay, not less. Now, there's only two outcomes in a hypothesis test. You either accept the null hypothesis and say, you know what, we don't have much evidence to ascertain the research hypothesis, so really the research hypothesis is not correct, and we cannot reject the null hypothesis. The coin is fair, or they did not cheat, or the dropout rate is 10%. We don't have any evidence against that. Or you reject the null hypothesis. You say, nope, things have changed in the population. Our belief in the population is no longer valid. We have to change our belief because this sample is telling us something different about the population. Okay? It's telling us something different about the population, because from the sample you would have deduced you would have inferred a different mean on the population, which is not what the mean that you believed in. Now, a hypothesis test never proves either hypothesis. There's no proof except in pure math. And even then, you'll be shocked to believe that, beyond the simple proofs we see in math, a proof in math is nothing more but a consensus because of axioms and the complexity of proofs in math, which is a little bit shocking, but that's as close as you get to a true proof. It's pure math, nothing else. You can't prove anything else in science, all observation and good statistical evidence, okay? You'll always get a black swan. So don't ever say that this proves it or this disproves it. You just say, do lawyer talk. Oh, we have enough evidence to believe that this is true, okay? So in a way, like, yeah, I never said this is true. I said we have enough evidence this is true. But that's the reality of the world, okay? Now, it doesn't mean you're like, you don't do the thing, like if some treatment is gonna help you and there's enough evidence for it, yeah, just go and do it. There's a likely chance, there's a small chance it might not work, but, in the absence of any other options, you do that, right? Okay, so, but we still haven't drawn the conclusion. I still haven't given you, all we've done so far is blah, 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 talking, and theory, and one number, that was the sample statistic. We have a sample, from it we compute a z value or a t value or something, right? We haven't done anything else. We haven't made a decision. Now it's the time to make a decision, okay? You draw a conclusion and to interpret the results. There's two ways we're going to draw a conclusion for a hypothesis test. The second way is what we did last time. We calculated the probability of getting 37% similarity score. If that was too low, then we say it's so rare, it's probably they've cheated. But the probability was so high, then like, no, they probably didn't cheat. Same thing with the coin, okay? So that's gonna be method 2, and we're gonna call that the p-value. Method 1, it's more intuitive, well, for some people, and it's what we call the rejection region. So, based on our significance level, if you convert that significance level to a z-score or a t-score, that's going to put you on a spot on the normal distribution or the t-distribution or the chi-square distribution, right? Because that alpha level is your probability that you've rejected a true null hypothesis. In other words, it's going to be the probability in the tails, and you'll see this in a second. But you can convert that alpha into a z-value. Then you take the z-value that you computed from your statistic and see if it's larger, then you're going to reject the null hypothesis. If it's lower, you're going to keep the null hypothesis. So we're going to define a region under the probability distribution based on the significance level. This would be a z-score or a t-score based on alpha. And that region is the rejection region of the null hypothesis. So that's where we're going to say, if any sample falls in that region, it's going to be so extreme that it's not a result of random chance. It's so extreme to get 30 heads on a fair coin, right? So getting 30 heads on a fair coin is really out in the outliers. Alpha tells you how far away you want to be, and then if your sample falls there, you're going to reject the null hypothesis, okay? And then you say, if our sample statistic falls in that region, then we reject the null hypothesis, otherwise we don't reject it. So thankfully, this is very easy to compute, and we've done that a lot of times so far, because we already have alpha, and alpha is nothing more than a probability. So to convert alpha to a z or t score is a simple inverse lookup, right? You take an alpha, are you in the left tail, on the right tail, or in the middle, right? You just go into your Google Sheets and get the t score or t value. So we have three cases. If my alternative hypothesis, I'm saying that the research hypothesis is that the actual population mean is less than what we assumed, then this is called a left tail test, and what you're looking for is the z-value where to the left of this z-value you have an area that's equal to your significance level. Did we do this? Yes, we did this a ton of times. Okay? This is nothing more than a normal inverse lookup or a t-score inverse lookup, right? So you say, inverse lookup for an area on the left equal to alpha give me this z-value. If your statistic, your sample statistic is here, you reject. So that's the benefit of converting our sample into a z-score, okay? In other words, if you were to convert this to an actual X bar score, let's say a mean value, you're saying, is the mean from my sample so extreme below any threshold mean? And I'm going to say, no, this is so extreme that I'm going to reject. We just converted things to a standard score to simplify the analysis. So if your z statistic falls here, if your sample statistic, because this is going to apply to t-scores and chi-squared scores as well. So if your sample statistic is here, you reject the null hypothesis. If not, you fail to reject the null hypothesis. The opposite case is when your research hypothesis is that the mean value or the proportion is larger than what your belief in the population is. So in that case, you're looking at a right-tailed analysis, and then you're going to find the z a probability or area to the right that's also equal to alpha, which is your significance level. Seriously, couldn't be easier, the mechanics. We've done all of this. And then if your sample statistic falls in that pink region, then orange region, you reject. Otherwise, you retain. And finally, we have one last case where mu is different than mu 0. That's kind of the hardest to conceptualize. In that case, you have what's called a two-tailed probability hypothesis test, where you split the tails into alpha over 2, and then you find the z values, this z value and this and that z value. Just pay careful attention that in the left and right tailed, the entire area on the right or the left is alpha. In the two-tailed test, you have alpha over 2. So as you're doing your calculations in Excel. Okay? So this is called a left-tailed test, a right-tailed test, and a two-tailed test. In other words, a left-tailed test when your research hypothesis is less than the population, the null hypothesis. The right-tailed test is when your alternative hypothesis is greater than the null, and not equal to the null gives you the two-tailed distribution. Now, this is nice and symmetric, and it's going to be the case for the t-distribution as well. So you really need to compute, one of these values. Okay. Now, in your sample statistic is going to give you one value. It might be here or it might be here. Okay. If it is, then you reject. If it's here in the middle, you don't reject the null hypothesis. Okay. So for our problem, the alternative hypothesis was that the actual proportion of students dropping out is less than 0.1. So this immediately tells you this is a left-tailed test, okay, less than. So I'm given the level, the significance level, alpha 0.02. I need to get the z value corresponding to this alpha to the left, not to the right, to the left. So I do z norm dot inverse of 0.02, so that gives me the left area. It gives me a z value of minus 2.054. Okay? This means that any sample statistic that is less than minus 2.054, we reject the null hypothesis. Again, because this is a left-tailed test. You're looking for less than. Okay? But our problem, the z value is minus 0.035, so we actually fail to reject the null hypothesis. So in other words, this is our significance level z value. So this alpha here is 0.02. This is the corresponding z value, minus 2.054. And our sample statistic is here. So we are not too far away from the assumed mean. Okay? When we standardized all of this, we made our belief in the population mean to be here, exactly at 0. Okay? When we standardized it. You're only asking how far away from 0 do I need to be to say this is so rare that this is wrong, that something else is going on. Well, here we're not too far. Our significance level is that you have to be in this region to say this is all wrong. Okay? Now, in physics, like I said, this alpha is 10 to the minus 16 or something. Okay? For most engineering applications in medicine, etc., you'll see alpha anywhere from 1% to 5%. Okay? So our sample statistic is outside the rejection region, and therefore we fail to reject the null hypothesis. And this means that we do not have sufficient evidence to say that the dropout rate is less than 10%. It doesn't mean it is 10%. We just, we don't have enough evidence. Maybe we need other sampling and keep sampling. But so far, we haven't challenged our belief. So the counselor has the burden of proof. He did not provide sufficient proof to say that the null hypothesis is to be rejected. Okay, so that's one approach. The other approach is what is known as the p-value approach or a probability approach. It's exactly what we did last time. You get a sample statistic, you calculate the probability of getting that sample statistic. If that probability is below your significance level, what you can tolerate, then you reject the null. If it's larger, you fail to reject the null, okay? That's it. So in the second method, we determine the probability. That's called the p-value. Some of you have heard of this p-value. So you read a paper, you know, oh, like this analysis was done with a p-value of 0.01, blah, 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 etc. I'm like, oh, well, what is the p-value? It's nothing more than the probability of getting this sample. If it's very rare, it's very small, it means what your assumptions about the population are wrong. Because you said, with my assumptions about the population, getting this result is so small, that doesn't make sense, because this result occurred, right? So it means my belief about the population is wrong, and something else is going on in the population, okay? Again, you have to make sure that you are given that the null hypothesis is true, okay? So if your probability of getting this statistic is less than your significance level, or how much you can tolerate, okay, how much you can tolerate to get 30 heads or 37% score, whatever, for cheating, okay? So if your probability of getting that sample is less than your significance level, you reject the null hypothesis. It means you are in one of those rejection regions, okay? You are in one of those rejection regions. Otherwise, if it's greater than the significance level, you fail to reject the null hypothesis. So for our problem, our sample statistic, which was the z-score, was minus 0.03536. And the fact that we are running a left tail test, we're going to calculate the probability that z is less than this value. That probability is 36.2%. Okay? 36.2% is much larger than 2%, which was our alpha, our tolerance, and therefore we fail to reject the null hypothesis. In other words, what we did here with the probability approach is we calculated the area. So this is our sample statistic. We calculated the area to the left, okay? Probability that z is less than this value. So it's this area. This area is huge. This is the area we were willing to say, you know, something is off about the population. This area is very likely. It's like even less than 1 standard deviation out of the mean. So you know what? We cannot reject the null hypothesis. And that's it. That's hypothesis testing. You know what we're going to do next? Yes?
Quick question. So the first method,
the rejection region.
Like when it's two sides.
When it's two-tailed,
Can it be both sides for those rejection regions, like when you do on a sample of the central?
So then in that case, it all occurs in the so the sum of the areas in the rejection region, that's still going to give you alpha. Now, in your case, when you're doing a p-value for a two-tailed test, you have to add up the probabilities. Okay, probability of the lab, because you're going to get a symmetric value, right? So what's going to happen, and we'll do an example with that. So let me explain it to you briefly. What will happen in a two-tailed test, you're going to get 2 z values for your statistic because it's symmetric. And then you're computing the area here and the area here. Their sum is greater than alpha or less than alpha. Yeah? Yeah. Good question. Okay. So then what the p-value represents is if the null hypothesis is true, what's the probability of observing the sample statistic? If that probability is so small, it means your null hypothesis is wrong. Because you shouldn't observe something like this randomly. You shouldn't observe, it's a very rare event. Therefore, your assumption about the population is wrong, and therefore, your population looks something entirely different, where actually your sample should be closer to the true population mean. Okay? So you're changing everything about your beliefs. All right, whichever method you use, so we'll take any method, rejection region or p-value in all papers, in a very large number of scientific papers, you'll only see the p-value. It's just easier to communicate. But I also want you to use p-hacking, to Google p-hacking. There's a technique, very bad people. They use a technique to hack the p-value and skew statistics so that they communicate a certain hypothesis that they want to communicate. It's a bad habit in statistics, unfortunately. It's hard to detect sometimes. It's called p-hacking if you want to look it up. If I have time at the end, we'll talk about it. So whatever method you use, you report your conclusion in the following way. Your conclusion to either reject or fail to reject the null hypothesis. What data led you to the conclusion? So you say the data collected from the 50 students, or collected in the lab, or the garage thermometer data led me to, you know, etc. Did use the z-value and whatnot. And then what it means to fail to reject or fail to reject the hypothesis in the context. You say we do not have sufficient evidence to say that the school dropout rate is less than 10%, okay? Or our conclusion says that we have sufficient evidence to reject the null hypothesis and say that the school dropout rate is likely less than the, you know, what we believed, okay? So let's do some examples first with some interpretation of hypothesis tests. So I'm going to give you the results so that you see, I'll give you the results from the end of the analysis, and I'll just help you draft the conclusion. So it's a couple of examples. At Northwest Mississippi Community College, the syllabi for online classes state that students should expect to spend 10 hours per week doing coursework for each 3-credit hour class. Okay? So one tip, as you're like going to interview for a job or taking a course, you're going to grad school, never ask, oh, how much time do I expect to spend per week on this? That's an immediate red flag. Everybody knows you have that question in mind, okay? But you are coming in fully on board, okay? You are coming, if you want to ask that question, try to extract it indirectly from, you know, one of the students working there, etc. But don't come in asking like, hey, how many hours am I expected to work per week? Because then there's the impression that this person is not gonna like love the job and appreciate it and, you know, put their heart into it, right? Although you're gonna work a reasonable number of hours, most likely, right? But just be careful when you ask that question. Okay, this is always a red flag, especially like with PhD students who are coming like to do grad work, right? Yes, you're gonna work 40 hours a week, but 40 hours you're barely gonna succeed. Okay, like every PhD student you go talk to every one of your professors who, you know, they've spent in like probably more than 24 hours a day. But what happens initially, you spend a lot of time, but then at the last few years you're on top of it, and then, you know, I have some of my senior students, they disappear for like a month. I'm like, hey, why are you still here, right? But, you know, they're faster, they're productive, etc. So anyway, just a note on the side, personal career advice. Okay. Instead, you should ask like, what are opportunities to spend more time on doing the work, right? So, you know, give that vibe. Okay, the director of e-learning for the community college is concerned that the students are being required to spend more than 10 hours per week doing work for each 3-credit course. A hypothesis test with a 5% level of significance is performed on the director's claim using, so the null hypothesis is that mu equal 10, and the counselor, or who is it? The director is saying no, they're actually spending more than 10. So they collected a sample, okay, and did the analysis, and the result of the analysis was a p-value of 0.014, right? So 1.4%. What's your conclusion? So our level of significance, what we could tolerate was 5%, but our result was 1.4%, okay? So our p-value was less than our significance level. Therefore, we're gonna reject the null hypothesis, because the probability, what we observed is that they are spending way more hours, and not just by chance, okay? So with a p-value of 0.014, which is less than the significance level, we reject the null hypothesis. We have sufficient evidence to supports the students study more than 10 hours per week on average, okay? So in other words, the sample of students we obtained, the number of hours per week they spent is so high that it couldn't have happened by pure chance. They are very likely actually spending more than 10 hours per week, okay? Now, a study on the effects of television viewing on children reports that children watch a mean of 4 hours. Yeah, definitely more. Well, with children, watch a mean of 4 hours of television per night. Well, I guess now they're on, screen. They should call it screen time because this could include, video games and things like that, right? So a mean of 4 hours of television per night. Kiko believes that the mean number of hours children in her neighborhood watch television per night is not 4. So she's not claiming more than 4 or less than 4. Like, it's definitely not 4. Some kids are doing like 1 hour. Some kids are doing 17 hours a day. Okay, it's really bad. So probably my kids are. I hope not. I don't think so. So she performs a hypothesis test. We have a really weird neighbor who comes and knocks on your door. Hey, I'm doing some hypothesis testing for the neighborhood. Will you give me how many hours your kids are watching TV? We're like, get out of here. So she performs a hypothesis test with a significance level of 10% with the following p-value. So she does the analysis, she collects a sample, etc., and she gets a p-value of 12.3%. But the significance level was 10%. Okay? So what does this tell us? The p-value is larger than the level of significance, which means the results of her sample are likely to have occurred by chance, so she cannot deny the null hypothesis. So because the p-value is greater than alpha, we fail to reject the null hypothesis. And the only thing you can say is, you cannot still claim that kids watch exactly 4 hours. You're like, I don't have enough evidence to say that they watch more or less than 4 hours. We just don't know yet. So far, maybe our belief that they watch 4 hours is still reasonable, is still valid, but we cannot, with the evidence we have, we cannot reject that they watch 4 hours. All right, one more thing I want to talk about is errors in hypothesis testing, and this will just be very brief because the details are very complicated. There's two errors that can occur in hypothesis testing. So what I have here is a decision matrix, let's say, and on the x-axis, or going column-wise, I have reality, if I knew what reality is, but this is reality, assume, and on the row-wise, or the y-axis, I have the decision of my hypothesis test. So in reality, either the null hypothesis is true or it's false, and my hypothesis testing is either going to reject the null hypothesis or fail to reject it. So if in reality H null is true and we fail to reject it, then this is the correct decision, right? And if the null hypothesis is false in reality and we actually reject it in our hypothesis test, so that's a correct decision as well. So those are in green. Now, type 1 error is when the null hypothesis is true, which you never know, okay? But if you knew that it was true, yet you reject it from your analysis, you've committed what we call type 1 error. And this is like, it's just not descriptive at all. Yeah, type 1 error, type 2 error. Like, why wouldn't they have called it something different? If H0 is false in reality, but you fail to reject it, that's called a type 2 error. Now, what's important for you to recognize is that the probability of committing type 1 error is what? Alpha. And that's something that you decide. Okay, so you obviously want to make alpha very small because I don't want to reject a true null hypothesis. I want to make sure that that probability is very, very, very small. And you're right in saying that. So you want to make alpha very, very small. Okay? However, the probability of type 2 errors is called beta. Again, completely undescriptive names. This beta we didn't talk about, but it can be computed, but it's very complicated to compute. But you should know that as you decrease alpha, beta increases, unfortunately. So you could say, I want to put an alpha of 10 to the minus 15. Well, in that case, beta is going to become on the order of 10 to the power 10. So you're going to more likely commit a type 2 error. Okay? And the way to think about it is on this kind of scale, balance. Well, as alpha decreases, beta increases. And as beta decreases, alpha increases. Where do you strike that balance? 5%, 2%, 1% have been okay, but there's always a chance that you're committing a type 2 error, okay, where you are failing to reject a false hypothesis, a false null hypothesis. Okay. All right, so we will start by doing the same thing we did with confidence interval. We're going to do a hypothesis test on a population where we know sigma, then we're going to go where we don't know sigma, then we're going to go to a proportion, and then we're going to go to variances. I will do in more details for the first case where we know sigma, because everything else is just changing the sample statistic and doing the same calculation over and over again. You're just doing either z or t or p or chi-squared. But the thought process is identical. We will build together a few Google Sheets. Maybe on the homework assignment, I'll ask you to build a couple of more calculators. We'll see. But we'll start with a population with a known sigma, and recall that the sample statistic, which was in the table earlier, if you know sigma, your sample statistic that you need to use to do the hypothesis test is the z-score, sample mean minus your belief in the population mean. I should put mu 0 here, over sigma by square root of n. N is your sample size, and sigma is in the known population standard deviation, which I know you don't know in reality. So next we will do the one without knowledge of sigma. And then you reject the null hypothesis if the test statistic calculated from the sample data falls within the rejection region. So for a left-tail test, this would mean your sample statistic is less than your critical z-value for where alpha is. And for a right-tail test, if your sample statistic is greater than that critical z-value. And for a two-tailed test, if your z-value is either outside or below those critical values, okay? And the types of hypothesis test, if it's less than the value, it's a left-tailed. If it's greater than your belief, it's right-tailed. And if it's different, it's two-tailed. So we saw this. And finally, the other method is the p-value approach, which is the probability of getting that sample statistic that you obtained. So once you calculate the sample statistic, you do a probability of z less than z or greater than z or between the two, okay? And then if your p-value is less than alpha, you reject. If it's greater than alpha, you fail to reject. All right, let's do some examples. First, the particle physics thing. What is this? I lied. I said 310 to the minus 16. It's like 310 to the minus 7, okay? But still, it's a very small p-value, okay? All right, so we'll start with one example. These are examples lifted straight out of your textbook, okay? So you can look back at them in detail and kind of study them. They're great examples. Really, once you do 3, 4, 5 of them, it just becomes a repetitive process, okay? So the State Education Department is considering a lot of focus on education in these examples today. Okay, the State Education Department is considering introducing new initiatives to boost the reading levels of 4th graders, okay? The mean reading level of 4th graders in the state over the last 5 years was a Lexile reader measure of 850L. So the Lexile measure is some company, some dude came up with, it's called My Measure, to measure your reading level. It's just a value, that says the larger the value, the more, the better of a reader you are, okay? The developers of a new program claim that their technique will raise the mean reading level of 4th graders above the current value. Okay, so what is my null hypothesis?
The new program will make the reading level of graders above the current.
So that's the alternative hypothesis, right? The null hypothesis is our current belief in the population that the mean reader measure is 850L, right? So that's our belief. These guys came in and said, no. We're going to make the reading score greater than that. So this also tells you that this is going to be a right-tail test. Agreed? So we're going to make the reading level of these students greater than the mean value. Okay, our belief in the mean value. To assess the impact of their initiative, the developers were given permission to implement their ideas in the classroom. At the end of the pilot study, a simple random sample of 1,000 fourth graders, great, because now we can use a normal distribution. 1,000 fourth graders had a mean reading level. So now they did a sample, and the sample mean, your X bar, is 856 L. It is assumed that the population standard deviation is 98 L, so you're given sigma for the population, and you're given a confidence level, a significance level of 5%. Using a 0.05 level of significance, should the findings of the study convince the education department of the validity of the developer's claim? Okay, that's the hypothesis. So are we gonna reject or fail to reject the null hypothesis? So let's see. Okay, first you state the null hypothesis and the alternative hypothesis. The null is that mu equal 850 L. The alternative is that mu is greater than 850 L. And always these two numbers are the same. So first identify the null hypothesis and then figure out if this is greater than, less than, or not equal to. Step 2, which distribution should we use? We have a sample of 1,000 students. We know sigma, so this is going to be a normal distribution. Okay? So then you get your sample statistic. Simply plug in the numbers. Your sample mean was 850. The population mean was assumed to be 850. And then you do your sigma, 98 over square root 1,000. You get your z statistic, your sample statistic. Z score is 1.94. Okay? Next, we're going to either reject, we're going to draw either a rejection region or a p-value. We'll do both. Okay? So we're going to draw a conclusion. Now, for the rejection region, to determine the rejection region, you go back to the, you want to calculate the z value that corresponds to the alpha that was given to you. So remember, alpha is the area and the tails. This is a right-hand tail test, a right tail test. Therefore, we're looking at the z value such that the area to the right is your alpha, 0.05. Now, whatever you use, you might use a right-tailed normal inverse normal distribution or a left-tailed. However you figure that out, make sure that you're computing a z value such that the area to the right is 0.05. You might be using a function that gives you a z value with area to the left. Then you give it the area to the left, which is 95%. Okay? But in whichever one you use, you're going to get this z score for this alpha. Okay? So now we know anything that belongs in this area is so rare that it means what we assumed about the population is wrong. And indeed, so our alpha value gives us this critical z score, which is 1.645, but our sample statistic was 1.94. So it belongs in this rejection region. In other words, the probability of getting that sample statistic is so rare, it means the population assumptions about the population are wrong. Okay, so the population looks different. So we're going to reject the null hypothesis. Okay, so indeed we reject the null hypothesis. In this case, we say we do not have sufficient. We have sufficient evidence to say that the average reading score has been improved by using this new program. Yes. Yes, so what we're doing, our sample statistic, okay, so the alpha, there's no formula for the alpha because we don't know the analytical formula. You have to use an inverse lookup. So what you're doing, you're going from alpha, which is the probability of making a mistake, this probability, to get the z score that corresponds to this alpha. And then it's a matter of comparing numbers. The only formula you're using is the one for our sample statistic. To go from alpha to a z value, you have to use Python or Google Sheets. There's no closed form formula for that. This is a nonlinear solver, okay? Or the z table, exactly. Z table or the PPF in Python or the inverse lookup in Google Sheets. It's really easy to do all of this in Google Sheets, so we'll do it after this example, okay? So the z value falls within the rejection region, so the conclusion is to reject the null hypothesis. Okay, method 2 with p-values. So p-values you don't have to draw anything, but you have to keep track in your mind of what you're doing, okay? So since this is a right-tailed test, then the p-value is the probability of getting z greater than or equal to our sample statistic. In other words, we're evaluating the probability to the right. We're evaluating this area, okay, from our sample statistic all the way to the end, because this is a right tail greater than. And if this area is smaller than than alpha, then we reject the null hypothesis. Okay. Now this is a cumulative distribution calculation, right? So you put in the normal distribution or whatever distribution you're using, and you give it cumulative and compute the area to the right, or 1 minus area to the left, right? Because cumulative distributions are always, you know, to the left, right? Some functions, some Google Excel on Google Sheets, sometimes they allow you to compute the area to the right. Just make sure you know what function, what routine you're using. You're using it correctly. But here you're computing the probability to the right of this number, or the area to the right of this number, okay? So now the area under the standard normal curve to the right of 1.94 is 0.0262, okay, or 2.62%. So that's our p-value, but our alpha significance level was 5%. So we are less than significance level. That's a very rare event that occurred. Okay, it's below our what we can tolerate, so it means something is wrong in our assumption about the population, and we're going to reject our null hypothesis. Okay? So in other words, the p-value is giving you this area to the right. Okay? Now you can do all of this in Google Sheets, pretty neat. So let's open up Google Sheets, and you're welcome to use these in your exam once we kind of build them up. Let me see here. All right. Okay. You can use spreadsheet. So go ahead and open up a new spreadsheet, because you're going to have to build one or two of those for your homework, I think. All right. So we're going to do, I'll help you do the first one, and you'll do the others. All right. Okay, so hypothesis testing, single population. Okay. Okay. So we're going to start by. I cannot. All right. Hold on. Let me drag this a little bit up. Okay. So for I know what to do. There you go. So I want to write here. So this is for known sigma. Because we're going to have one for unknown sigma, we're going to have one for proportions, and one for variances, okay? So this is really doing means, mean with known sigma. Okay. So what I need is for inputs is my null hypothesis, so the assumed mean, or null hypothesis, or H0, say H0, okay? And that's going to be a value given to me. So let's say here, just to punch in some numbers, 850. Okay? And the sample mean, so that's x bar, okay, which was 856 in this case. Okay? The population sigma, standard deviation, which was 0.8 in this case, just to punch in some numbers so I don't get nans. Sample size, what was it? 1,000. Okay, sample size n, that was 1,000 in this case. My significance level, alpha, and we're going to do here 5%. So right for the example, 0.05. Okay, and you can modify this however you like, right? Okay, so the first thing I want to do is my sample statistic. Okay, so sample statistic. So you can format this however you like. So you know you can lock certain cells or give them different colors to indicate that this is input and this is output. Okay. So the sample statistic is simply, in this case, it's always going to be a z-score, which is x bar minus mu over square root of sigma over n. Correct? So this is going to be, let's see. Okay, so I wish we could use like variable names in Google Sheets. I don't know if there's a way to do that. It's going to be x bar minus mu, so I'm going to put parentheses around them, over square root of sigma over n. No, sorry, over b over square root of n. Sigma over square root of n, not square root of sigma over n. Ah! Come on, don't delete everything. Okay, my bad. Me. See, I also forget formulas. Okay. So sample statistic is equal to sample mean x bar minus mu over sigma over square root of n, square root of the sample size. And I made a mistake. This should be not, yeah, this should be B4 here, right? Huh? No, that doesn't make sense. B2 x bar minus mu over B3, which is sigma over square root of B4. Oh, sorry, 98. Ha, okay, that makes sense. 98 was the standard deviation. My bad. Okay, good. So now we will start, we're going to build this together. We're going to start with what I'm going to do a left-tailed test, left-tailed, right-tailed, and two-tailed. So we'll start with the left-tailed because that's the example we just did. So for the left-tailed or the right-tailed, we need to calculate the critical values, right? And the critical value on the left-tailed is the area to the left is the z-score where the area to the left is alpha, and the right-tailed is the z-score where the area to the right is alpha. So we're going to do critical value. So we'll start with this right-tailed, right? So if you remember what we did, let me move my window here, my slide. So in the right-tailed test, now this is my critical value, is the z-value such that the area to the right of this value is equal to alpha. Okay, so I get this from norm.inverse. Okay. So for the right-tailed, this is going to be norm. The only function I have here is norm.standard, so inverse standard normal distribution. Okay, now this distribution always computes the area to the left. It gives me the z-value such that the area to the left is whatever number I give it. Okay? So I can either give it the area to the left, which is 1 minus alpha, right? And then it's going to give me 1.64445, right? Okay? That's the right-tailed. Okay? Now, by the same token, since I'm at it, I can also implement the left-tailed. And for the left-tailed, it's going to be norm.s.inverse alpha. Okay? And indeed, because it's symmetric, those two values are going to be the same. Just one of them is going to have a negative value. The other one is going to have a positive value. Okay? Leave the two-tailed for a second. We'll do it later. Okay. Next, I'm going to calculate the p-value. My p-value is going to be the probability of observing my statistic. Okay? So it's going to be the probability of z greater than or equal to 1.94. Now in Google Sheets, in Excel might be different, other tools might be different, but I know in Google Sheets that I'm on the CDF only computes areas to the left. So it's going to give me the area from minus infinity up to 1.94. To get the area to the right, I need to subtract it from 1. It's 1 minus that. Okay, if you remember, we did this early on. So for the right-tailed, I'm going to do this equal to 1 minus normal dot s dot distribution. So this gives me the standard normal cumulative distribution. Okay, it's simply an x value. What x value do I need to put here? My sample statistic, right? That is the probability of observing this value or greater. Okay? Make sense? If I then put 1 minus, it will give me the area to the left of that z value, which is not what I want. Because by definition, that norm.s.distribution gives me cumulative up to that value. All right. So now we need to make a conclusion, and this will be cool. Conclusion to either reject or fail to reject. Okay? So what I'm going to do here, I'm going to say if statements in Excel or Google Sheets are pretty simple. If logical expression is true, then if logical expression, whatever, greater than, less than, etc., comma, value if true, comma, value if false. So my logical expression is if my p-value is less than alpha, reject, otherwise fail to reject. Agreed? So if my p-value, which is here, is less than alpha, then what we're going to do, we're going to reject. Otherwise, we're going to say fail to reject. This is pretty cool. It's telling me to reject. Okay? It's telling me to reject. Okay? So now we can do the same thing. So these are the numbers for this case, right? So let's do another example with a left-tailed distribution. Okay, but before that, let's do a confidence interval. Okay. Now, we can also build a confidence interval for our sample statistic, and that will give us one more reassurance whether we got things right or wrong. Okay, from our sample statistic, we're going to build a confidence interval. If our result was to reject the null hypothesis, then our confidence interval is not going to contain the null hypothesis value by definition, because it belongs to a different population. If we fail to reject the null, then our confidence interval is going to contain the null hypothesis. So it's a good way to reassure ourselves that yep, things are good. So the way we're going to build this is we're going to use the critical z-value, okay? The critical z-value with the sigma over, so the standard definition of the confidence interval, okay? Why use z-critical rather than the sample statistic? Because we made an assumption on the population. So we have to use the z-value that corresponds to that confidence level, okay? So we can build this here. I'm going to do an error here. So we're going to do an error. I'm going to call this the error. And so that error is simply z critical times sigma over square root of n. So that's going to be equal to z critical, right? That's the critical value, times sigma over square root of n, right? And that's going to be 5.097, whatever. Okay, and then confidence interval. Okay, so let's come here and say confidence, or CI for one-tailed. And my confidence is going to be x plus or minus that error. So it's going to be equal to x bar minus that value, and then x bar plus that value. And indeed, my confidence interval is from 850.9 or 851 to 861, does not contain 850. So in other words, if I were to just collect that sample and build a confidence interval on it, it does not contain 850. Tells me that the population mean is definitely not 850, which confirms our result that we reject the null hypothesis. Now, why did I put this here under the left tail and the right tail? Because they're going to be the same result, as we will see. Okay, so let's continue and do a left tail test. See how much time we got. We're almost out of time. A researcher claims that the mean age of women in California at the time of completing a master's degree is less than 26.5 years. Surveying a simple random sample of 213 women in California who completed a master's degree, the researcher found a mean age of 26 years. Assuming that the population standard deviation is 2.3 years, and using a 99% level of confidence, determine if there's sufficient evidence to support the claim. So our null hypothesis is 26.5 years. And the researcher is saying that the actual age is less than that. And in their sample, they got 26 years. Okay? So now we know that H null is mu equal 26.5. And our alternative hypothesis is mu is less than 26.5 years. Okay? So therefore, this is going to be a left tail test. Okay? And with the left tail test, we're going to look at the area to the left side, in the left tail, so area less than. And again, we'll do the same thing. We're going to do a rejection region and a p-value. Now, in this case, we were given the level of confidence, which is 99%, not 95%. My apologies. I don't know where this came from. Is 99%. So the level of significance is 1 minus the confidence level, which is 1% or 0.01. Okay? It gives us alpha. So next we do the sample statistic. It's simply x bar minus mu over sigma or square root of n. So we did this. It's minus 3.17. That's a dimensionless, unitless quantity. Okay? And then finally we're going to draw conclusions. So rejection value, rejection region is based on the significance level. Okay? So you take that confidence level, or alpha, which is 1%. What is the z value that corresponds to an area on the left that is 1%? Okay, so in other words, go and do your inverse lookup and find the z value such that the area to the left now is 1%. So this should be 1% here, 0.01, sorry. So not 0.05, mistake. So you get a z critical value, but the sample statistic is less than that. So it's in this rejection region. So we're going to reject the null hypothesis. Okay? So I'm going to do this in our code, in our Google Sheet, because we're really very close to this. So in this case, my assumed mean was 26.5, right? And the sample mean was 26 years. The population sigma, what was it? The population sigma was 2.3 years. So 2.3. The sample size was 213 women. So 213. The significance level was 1%, so 0.01. Okay? And 213, etc. And so that gives me my sample statistic of minus 3.17, which is what I got over here. Okay? So now we're going to do this with the left tail test. We already have the critical value, which is minus 2.32. So I can tell immediately that this is smaller than that, so we're going to reject. But let's also do a p-value. So in this case, the p-value is the probability of getting z less than this critical value. So this is going to be equal norm dot s dot distribution, cumulative, of getting this value. Okay? And that gives me 0.009999, very small probability. Okay? A p-value. Now my conclusion is going to be the same as this guy. I'm going to copy and paste this guy here. And we're going to say if E3, if this value, so if E3 less than my significance level, we're going to reject the hypothesis. Okay, indeed, we're going to reject the hypothesis. In this case, the error is the same thing. It's Z critical, so the error is the same thing as this guy. Doesn't matter because that's going to be equal to the absolute value of Z critical because that's negative times standard deviation over square root of n. And it's going to be the same value. And my confidence interval is 25.6 to, no, hold on. We're going to reject the hypothesis and, yes, okay, yeah. So our confidence interval is between 25.6 and 26.3. It's less than what we assumed, that the population is 26.5. So indeed, we reject the null hypothesis that we have sufficient evidence to say that the mean age for women graduating with master's degrees is less than 26.5 years. Okay? All right, I'll let you go. We'll see you on Thursday. Godspeed.